Okay, hello. I'm a computer science PhD student at the University of New Mexico. And over the past year, I've been collaborating with Livermore Lab scientists, and Johannes Dorfert, studying machine learning optimizations for scientific computing. There's an abundance of prior reporting on using machine learning for performance prediction, as well as performance optimization. Our study followed some of this motivation from the current literature, one in targeting the OpenMP offload capability provided by LLVM, given that all major hardware vendors support it, and two, using machine learning to predict optimal configurations. So official support for OpenMP offload project began with the LLVM 15 release, where developers could access the offload capability through the target pragma directive. Here is a C++ and Bash code snippet invoking the directive to offload a simple vector addition computation. Launch configurations can be set using clauses in the code or via environment variables, as I do here in the Bash script. If not provided by the developer, default launch configurations are used. Now I'll share some visualizations from results from a 100 trial randomization experiment using a Hexi bench suite OMP benchmark. Here is a histogram displaying the resulting distribution of our relative performance execution times, where a majority of the values are within 10% of the fastest execution line. So we'll call those values to the left of the red dashed line optimal and to the right suboptimal. Here is a scatter plot of the varied launch configurations with threads on the x-axis and blocks on the y-axis. The optimal configurations are in green and the suboptimal are in transparent red. And here we can see that if the developer chooses values for the number of threads less than 256, there's a high probability of selecting a suboptimal configuration. And here's a 3D surface plot of the same parameters. The green surface area identifies configurations that are within that 10% of the fastest time. And it is this space that will need to be investigated by the developer, squarely putting the optimal performance on his or her shoulders. So some common practices for finding an optimal configuration include guided tuning techniques and machine learning, which can be both time consuming and resource intensive. The goal of our study was to address this challenge by investigating machine learning approaches to reduce the time and cost of identifying an optimal launch configuration, the benefits of which could be applied to both a single execution of code or multiple. So for instance, a scientist running a scientific experiment or an engineer attempting to optimize a scientific application by using guided tuning techniques. So we began our predictive model with data collection and curation from multiple offload application executions. Next, we took the information we gathered, both compile time and runtime, and created training data using feature engineering techniques. And in the final step of the workflow, we made optimality predictions. So early on in experimentation, we discovered that a benchmark's performance distribution had fundamental implications to prediction. Hence, we investigated a two-stage prediction model, where in the first stage, we first predict the performance distribution shape of the application sample, and based on that shape, in the second stage, we predict optimality of the sample's configuration. So we began our two-stage prediction workflow with data collection and curation. We started by compiling 101 of the 321 available OMP benchmarks from the Hexi bench suite, then executed 100 simulations per benchmark. From the compilation outputs, we parsed static information, such as direct call count and max loop depth from the function property analysis pass outputs. and general purpose register values from kernel resource usage remarks generated by the OMP pipeline. From the execution outputs, we parse dynamic information such as teams and trip count from the OMP runtime, as well as execution time and kernel calls outputs by the Rockcroft tool. So our data collection generated 10,100 instances with 114 total features that we then curated into feature vectors and then correlated them into a CSV file for machine learning pre-processing. So for each sample executed, we stochastically varied the launch configurations. Shown in this slide are the heuristics we use. Get block sizes, return an array of values consisting of multiples of the wavefront size and uniformly randomly selecting values with replacement bounded by the wavefront size and the workgroup maximum size. The get num blocks return a single value, stochastically calculated between a lower bound of 240, which number of SIMBs we use, and an upper bound value equal to the trip count divided by the block size. The launch configurations that were generated by the previous code for each sample executed was set in OMP runtime by using environment variables. In order to set configurations, we edited code in the getNum blocks and getNum thread functions of the generic kernel class defined in pluginterface.cpp in the offload project. We also replaced the developer configuration entries in order to obtain a baseline for comparison. And on this slide is code that we use to output compile time information. First highlighted is the pass builder class function, located in the core LLVM package, I believe, where we added code to output the function property analysis pass information. And below that, the CLane configuration parameters used to output kernel resource usage remarks during compilation. So in step 2 of our workflow, we utilize feature engineering to generalize our models. The step I will highlight is the feature creation step. Since our goal was to predict performance execution time, the original target feature of our prediction was total duration nanoseconds reported by Rockcroft. However, we were training our models using multiple applications, range from simple to larger proxy apps. Therefore, we created a new feature called relative performance execution, which is defined as the execution time of the benchmark sample total duration nanoseconds relative to that benchmark's fastest performing configuration, thereby predicting rank performance instead of execution times. Shown in the 2 scatter plots to the right are lunch parameters, threads and blocks versus the new relative performance metric. And after creating this new feature, we discovered that benchmarks distributions of these values had significant implications to performance prediction. The resulting distribution of values followed groupings, actually. And we discovered that prediction can be significantly improved by training models for each group of kernels. So next we added descriptors that characterize these groupings, which included distribution shape, outliers, spread, and center. After feature creation, we followed some established steps for preparing our data. For training, we removed non-relevant features and leakage features. We transformed our data, which consisted of float and integer values that varied in size and range. One technique typically used is normalization, which prevents bias towards features with larger values, improve numerical stability, and improve conversion speed. However, in our case, we accomplished the same outcome using discretization and binning. And then the last step of feature engineering, we generalized the models using feature reduction and regularization techniques. So the final step of our workflow was relative performance prediction. Given that we desired to produce optimal configurations, we needed a machine learning model that was transparent and interpretable. allowing us to reproduce the decisions that could lead to an optimal configuration prediction. Hence, we chose decision tree models. We initially attempted regression modeling, however, the models did not generalize well, so we switched to a classification problem. So with our data pre-processed, we trained our models. For stage 1, the target feature was the distribution shape, and it was trained on all data, while the stage 2 models with the relative performance target feature were trained on data segregated based on application distribution shapes. Next was the model prediction. For stage 1, there were 2 shape labels predicted, left skewed or right skewed. And for stage 2, there were 2 optimality labels based on relative performance, optimal and suboptimal. Optimal is defined as a relative performance value within 10% of the best performing benchmark configuration, while greater values were labeled suboptimal. Using a 2-stage approach, remove the level of uncertainty by predicting the distribution characteristics of the sample first. And this allowed the next stage models trained on an individual distribution group to make an informed optimality prediction. So for our experimental setup, we use a supercomputer cluster at Livermore Labs. Each compute node on the test cluster had a single 48-core AMD ROM CPU and 8 AMD MI50 GPUs. We generated our training data using 8 nodes and our predictions using 1 node. And in total, we had 7 run configurations for experimental treatments. And in each experiment, we varied the classification type, number of benchmarks, number of decision trees, and the number of prediction stages. So overall, we observed that the 2-stage binary classifier case performed the best. And here's the model's performance for unseen instances evaluation. In this test, we used a holdout 80-20, where samples were shuffled and split, and 80% used for training and 20% used for testing. In this panel A, you see confusion matrices. The columns contain values for predicted classes, and rows contain the actual or truth classes. Starting with the matrix on the left, this matrix is column normalized, showing the distribution of predictions. And this shows the model's performance in avoiding false positives or precision. And for the 2-stage binary classifier, we had a 94% accuracy for optimal case predictions, only misclassifying 6 of the test instances. The right matrix is row normalized, showing the performance per class. So this shows the model's performance in finding all true positives for the recall measurement. And here we observe that our model captured 87% of the optimal test instances while failing to identify 13%. And here are those same, some of those same performance measurements listed in a table. The confusion matrices above are simply another way of visualizing these measurements. The performance measurements include precision or avoiding false positives, shown in the left confusion matrix. Recall or finding all true positives, shown in the right confusion matrix. And F1 score, that is a weighted harmonic mean of precision and recall. And support, which is simply the number of test samples used for each class. And in panel C, we have predictions per stage, per decision tree, using stacked bar plots. Here we can see the number of test samples or support that was sent from stage 1 to the stage 2 models. The left skewed model received a larger proportion of the suboptimal instances to classify, and vice versa for the right skew model. And as hypothesized, the performance prediction models in stage 2 had very high precision accuracies, having been trained on a respective data group of kernels. The second evaluation was an unseen benchmark test, where all samples from the selected benchmarks were withheld from training and used as test data. Shown here are the prediction accuracies for 4 selected proxy apps plus 4 randomly selected apps. The 4 proxy apps were LavaMD, Su3, Pathfinder, and XSBench. And here we observe cases where the model failed to correctly predict almost any sample from the app, yielding a very poor accuracy score. And in other cases where the accuracy was extremely high. We identified that in these extreme cases, the samples from an application were profoundly skewed with fewer than 5 test samples in one of the actual classes. And in the case of Su3 and LavaMD, only 1 test sample in one of the actual classes. So those situations lead to severe class imbalance. I mean, those situations have a severe class imbalance, which leads to degenerative predictions. So as you can see in the Su3 and LavaMD, this can be either good or bad. It simply depends on if the stage 1 model accurately predicts the application's performance distribution shape. And so we view this unseen benchmark evaluation as closely exemplifying how we anticipate our 2-stage prediction model being used as a surrogate model. And with that, I'll conclude. Essentially, there do exist machine learning tools for configuration prediction, optimal configuration prediction, but none to date have targeted OpenMP for integration. In our experimentation, we collected 10,100 test instances for training using 101 OMP benchmark apps and collecting 114 static and dynamic features. We discovered that relative performance of a benchmark was very important. So we created features to capture it and added an additional prediction stage in our modeling. The best performer from experimentation was the 2-stage binary classifier model. When predicting an optimal configuration, we achieved a precision of 94% accuracy and a recall of 87%. And the unseen benchmark evaluations is how we anticipate our model being used as a surrogate. And with that, I will take any questions.
Let's thank our speakers. Questions?
First of all, do I understand correctly that basically the input to the model is the code and the configuration, and then the model tells you whether that's optimal or suboptimal? Is that right?
Correct.
What will it take to make this more practical? Like, I give the model the code, and then the model tells me what is the good configuration.
That would be similar to the unseen benchmark evaluation, where we trained the model. So we had 101 different benchmarks. For that unseen evaluation, we took that benchmark completely out of the training data. So it had been completely unseen to the model, and we evaluated on that unseen model. So for instance, in your case, like what we're doing right now with the real world scientific application of OpenMP, is that we're evaluating it using our predictive model to tell us optimal or suboptimal configurations.
Okay, the code, that's a comment. You may want to repurpose the model instead of a binary classifier to actually be a generator on the number of teams or threads or whatever they want.
Okay, so you're correct. So our current work is working on a configuration advisor.
Okay.
And that configuration advisor will take the model, and it basically, at this stage, we're looking at whether to use the predictive model in a loop or another form of modeling to kind of reverse that. So where you actually actual optimal and you get the configuration.
Mm-hmm. You might want to look at that as well. It's a network work, it's an archive. Okay. And they try to do similar things where the user gives the features instead of trying to auto extract them. Mm-hmm. And then the model, it builds like a decision tree model that tries to find the configuration. So it might give you some inspiration there.
Okay. You said, did you
adaptive OpenMP?
Thank you.
Any other questions? Let me check. Okay. Couple couple of questions.
Okay.
So both your training and test data is from Hackbench.
Correct.
Okay. And when you're just wearing seen, unseen, and you retrain every time you do that partition.
For the unseen benchmark, we do retrain and retrain. We pull one out, we retrain, and then we test the one that we pulled out. Correct.
Okay. And how much time does your training take?
Fortunately, these HEC benchmarks are pretty quick. In order for me to retrain, we already have the data collected. I think that was the most expensive time, running the 100 simulations per what have you. But with that feature CBS trial, we can retrain instantaneously. Training only takes about a couple minutes.
Okay. How many GPUs do you use for that?
For the model prediction, we use one GPU actually.
Sorry, that was more than one question. Okay, if we don't have any more questions, let's thank our speaker once more.